program counter is a special type of counter used in a CPU. So you'll see this referred to as PC, so don't get confused by personal computer. In this context, when we say PC, we're talking about the program counter. So a program counter stores the address of the next instruction that will be executed. So the next instruction that's going to get fetched and then executed by the computer. So typically, this might just be the next instruction in memory, so no computers can just execute these instructions sequentially. So we might just start on instruction 0, 1, 2, 3, 4, 5, 6 and so on. So in this instance, we want to increment, we need to be able to get this counter to increment by a value of 1. We also want it to be able to jump to another instruction, because for example, if you're doing an if-else statement in C, if a particular condition is true, you might want to just execute the next instruction in line, but if it's false, you might want to jump to a different instruction. So if this is true, execute or fetch instruction 7. If it's false, you might want to end up being kind of instruction 35 or something. So sometimes we need to jump. So if we want to jump to another instruction, this essentially just means we need to load a new value into the counter. So the counter, in normal instances, just counts up 1, 2, 3, 4, 5, 6. Then if we just load a new value into it, so the value can either be bigger or smaller, we just load a new value and then it'll start counting from that. So this is what we call a jump. And then in some cases, we also want to reset the counter back to 0. So we're just going to start essentially the program again. And then if we don't do any of them things, in some situations, we might just want to kind of halt the program essentially just by holding the value. So the program counter in the hack computer is a 16-bit counter. So these are the values we can count, saying 0 to 65,535. So it's implemented using a 16-bit register and then some combination of logic that you've already built. And it's actually very important that you get the precedence of the operations and the API correct. So the correct order is reset, load, increment and hold. So we'll look at the kind of block diagram of the program counter. Again, we've got our input value, so we can load a new value into the counter, assuming that the load bit is 1. So if the load is 1, we'll load a new value in. Then if the increment bit is a 1, whatever value is current on the counter, so if it's 66, it'll go on to 67, 68 and so on. So as the clocks come in, so we can see we've got a clock input here. So as the clock ticks, the value will increment, assuming that this increment is high. We can also reset. We set this pin high, the counter will reset back to 0. So you just need to be very wary of the operations in the API. So we can see this is just like a else if statement in C. So reset is a kind of top priority one. So if reset is true, then we make the output go back to 0. Else if load is true, and we just set the new value from the input. Else if increment, then the output just increases by 1. And if we don't do any of those, we just hold and the output stays the same. So in this situation, if all these bits were 1, so trying to select all of them at the same time, it's actually reset. That takes priority because this is at the top here. So this shows the order of priority and it corresponds to reset, load, increment and hold. So we'll look at an example. So we'll just assume, so we can see we've got a clock signal along the bottom. And we're going to assume that when we first start looking at this timing diagram, the output is 47. So in this cycle, all of these inputs, so the reset, load and increment, they're all 0. So because they're all 0, it means it's holding, and that value just holds and it's still 47 in the next clock cycle. But now, when we look in the next clock cycle, that's a reset is now a 1. So reset, we know, is a highest priority operation. So in the next clock cycle, this will take a count, and 47 was the old value of the still on the counter, and now it's reset back to the zero. Now it's reset back to 0, and again we can see, go back to that hold, because at this point in this cycle all the inputs are all 0, so we just hold 0, stays to 0. And then in this clock cycle we can see that increment has now gone high. So from this entire period you can see that increment is high, so the clock in Everec is just going to go 0, 1, 2, 3. But now when it gets to this point, load is also a 1. So in this cycle here, load is also a 1. So increment is 1 and load is a 1. But from the previous slide we know that load takes precedence. So we're going to load in the new value. So all along the value 527 has been on the input, so that value is on the input. So it's only now in this cycle when load becomes 1 that this value then will be loaded into the counter. And again in the next clock cycle, load is no longer 0, but increment still is a 1. So we'll just carry on incrementing like we saw before. And it's just when we get back to this cycle, where all the input bits go to 0, I would just start holding again, and this just stays the same.